Welcome to the pre-course lecture of Module 8 of the summer school, which is about clustering or cluster analysis. My name is Kristin Tøndel. I work as a professor in data science at NMBU, and I will be teaching this module this summer. I will now give a summary of the contents of this module. So, what do we mean by clustering or cluster analysis? Well, clustering is organization of unlabeled data into similarity groups that we call clusters. With unlabeled data, we mean that we have only one set of data. We don't have any response variable that we relate the data to. A cluster is a collection of data items which are similar to each other and dissimilar to data items in other clusters. So cluster analysis is an unsupervised learning method, which means it doesn't involve any prediction or classification. We only deal with one set of data, and we try to find patterns in this data. So if you look at these two pictures on the bottom of the slide, it's easy to see by the eye that there are two collections or groups of samples. We have one group in the middle, and we have one group of observations in a circle around. And to the left, you see an example of a good clustering result, where the algorithm has succeeded in finding the correct pattern in the data. While to the right, you see a bad clustering result, where the algorithm has separated the observations in a way that doesn't correspond to the natural pattern in the data. Common roles that clustering can play is, for example, in data reduction, where we try to reduce the information from an entire population of samples to information about specific groups. Clustering can also be used for hypothesis generation, for developing hypotheses concerning the nature of the data, or examining previously stated hypotheses. Examples of applications are in medicine, where we can use clustering for characterization of patients on the basis of clusters of symptoms in order to identify an appropriate therapy. It can also be used in biology, for example, for finding groups of genes that have similar functions. And clustering has been used in climate research for finding patterns in the atmospheric pressure of polar regions and areas of the ocean that have a significant impact on land climate. I'll now say a little bit about the differences between clustering and latent variable approaches, such as PCA, and the differences between clustering and discriminant analysis. In clustering, the grouping is based on the distance or proximity between the samples, while in latent variable approaches, such as PCA, the grouping is based on patterns of variation in the data. In clustering, you don't know which objects that belong to which group, and often not even a number of groups. While discriminant analysis requires you to know the group memberships for the cases used to derive the classification rule. So in discriminant analysis, we try to derive a prediction model that can predict the group memberships for new data points based on what we know about the data that we use for deriving the rule, the classification rule. So in discriminant analysis, we deal with two sets of data. One set of descriptors and one set of group memberships. So discriminant analysis is a supervised learning method, while clustering and PCA are unsupervised learning methods where we deal with only one set of data. So what do we need for clustering? Well, in clustering, we must address three basic questions. One, how do we measure similarity between the samples? And two, how do we form the clusters? And three, how many groups shall we form? How many clusters are there in the data? We therefore need a proximity measure, either based on the similarity or dissimilarity between the samples. We need a criterion function in order to evaluate the clustering, and we need an algorithm to compute the clustering, for example, by optimizing the criterion function. I'll now say a little bit about similarity measures. And distance measures are the most often used measures of similarity. Here, higher values represent greater dissimilarity rather than similarity. So here we calculate the distance between the cases. We also have correlational measures, which are less frequently used. And here, large values of the correlations indicate similarity between the samples. Now some examples of similarity measures. The most commonly used distance measure is the Euclidean distance. This Euclidean distance is the sum of the squared distances between the samples, where we take the square root in the end. We can also use the squared Euclidean distance, which is the sum of the square differences without taking the square root. A third similarity measure is the city block or Manhattan distance, which uses the absolute values of the differences. There are many other similarity measures as well, so these are just 3 examples. So, over to the question of how many clusters we should form. If we look at these data points here, we can see to the left, if we are very strict on how similar the samples should be in order to be in the same cluster, we can say that there are 3 clusters in this data. Or if we are a little bit less strict, we can say that there are only 2 clusters. Possible approaches in order to find how many clusters we should use is to fix the number of clusters, which is typically something we do if we have an idea beforehand of how many groups there should be in the data. Or we can find the best clustering according to the criterion function. And a common way to do this is to vary the number of clusters, evaluate the criterion function, and plot the values of the criterion function against the number of clusters in what we call an elbow plot. Then we can see what would be the optimal number of clusters. In clustering, as well in many other data analysis methods, outliers is something that we have to pay attention to. And it's important to think about whether we should remove outliers or retain them. Removing outliers creates a risk of losing important information, while if we retain outliers that should have been removed, for example, if the outliers are caused by measurement errors, then the outliers can confuse the clustering algorithm and give us a wrong result. So, in general, outliers should be removed if they represent atypical observations that are not representative for the population, or if they are observations of small or insignificant segments within the population that are of no interest to the research objectives. Outliers should be retained if we have an undersampling or a poor representation of relevant groups in the population. Then the sample size should be increased in order to ensure representation of these groups. So how can we detect such outliers? Well, we can detect them based on the similarity measure by finding observations with large distances from all other observations. We can also see them in graphic diagrams that highlight outlying cases, such as box plots. And we can see them by their appearance in cluster solutions as a single member or very small clusters. In clustering, in the same way as most other data analysis methods, standardizing the data is important. Clustering variables that have widely different scales or exhibit large differences in standard deviations should be standardized. And the most common standardization is to use the set score. That is, subtracting the mean and dividing by the standard deviation, so that all the variables get to the same scale with mean equal to 0 and a standard deviation of 1. Then all the variables have the same chance of contributing to the clustering model. There are a number of different methods that can be used to carry out a cluster analysis. These can be classified as follows. We have hierarchical cluster analysis, we have non-hierarchical cluster analysis, and we have a combination of both methods. There are other ways that clustering methods can be classified as well, but this is the scheme that I will use in this lecture. So a little bit about some main differences between hierarchical clustering and non-hierarchical clustering. Hierarchical clustering is also called connectivity-based clustering, and here the final clusters are built following a distinct set of sequential steps. This can be done either by the agglomerative approach, where samples are connected together in clusters sequentially according to the similarity between them, or we can use the divisive approach, which goes in the opposite direction, where clusters are formed by splitting up sequentially the samples into smaller and smaller clusters. Non-hierarchical clustering is not done in a sequential manner in this case, like this. This means that if M clusters are built using non-hierarchical clustering, there is no guarantee that putting together two of the clusters would give rise to the same M-1 clusters built separately by the method. Examples of non-hierarchical clustering approaches are centroid-based clustering, such as, for example, k-means clustering, distribution-based clustering, and density-based clustering. Now go through briefly how these different methods work. Connectivity-based clustering, or hierarchical cluster analysis, presents a hierarchy of clusters represented by a so-called dendrogram, where different cluster solutions appear at different similarities or distances. If we look at these 6 samples here, A, B, C, D, E, and F, we see that A is alone up here, B and C are quite close together, D and E are also quite close together, and F is close to D and E, but further from them than they are from each other. So if we start out with each sample belonging to a cluster by itself, we see that B and C are the closest ones together with D and E. So we gather those together in clusters. If we are less strict than this for when we evaluate which objects should be in the same cluster, we can say that A is alone, B and C form a cluster, and D, E, and F form a cluster. Then we get D, E, and F here. We put F together with D and E. We have B and C, and we still have A by itself. If we are even less strict when it comes to how similar they should be, we can say that this is one cluster. All these 5 samples belong to the same cluster, and we have A alone as an outlier. Then we get the cluster solution like this: A and B, C, D, and E, and F. And the other extreme is all samples belonging to one cluster. So by doing this, we get an overview of different cluster solutions appearing at different distance thresholds. This gives us the overview to choose how many clusters we should use, because we can see the different configurations appearing at different distance thresholds. This sequential approach leads to that objects that belong to a child cluster also belong to the parent cluster. As we can see here, we can clearly see that A is very far from the others. A is never connected to any of the others apart from the extreme where all samples belong to the same cluster. So hierarchical cluster analysis is also useful for identifying outliers. Another commonly used clustering method is centroid-based clustering. And here clusters are represented by a central vector, or a centroid, which we also call it, which can, for example, be the mean of the variables within each cluster, such as in k-means clustering. And if you look at this figure to the right, we see these centroids or cluster centers as crosses. And these are often initialized at random and then updated iteratively based on calculating the mean of the samples belonging to the clusters. A variant of k-means clustering is called fuzzy c-means clustering. And here objects may belong to more than one cluster, so that each observation has a certain probability of belonging to each of the clusters. Distribution-based clustering models clusters based on statistical distributions, for example, multivariate normal distributions. If you look at this picture, we see that there are 3 clusters, and each of them have separate multivariate normal or Gaussian type statistical distributions. A drawback of this approach is that for many real datasets, there may be no concisely defined mathematical model. In density-based clustering, clusters are defined as connected dense regions in the data space. If you look at this picture, we see that in these 2 clusters, the data points are packed densely together. And there are some points outside of these regions. And in density-based clustering, these are defined as outliers. An example of a density-based clustering algorithm is dbScan, which connects points with a minimum number of other points within a certain radius. So the min PTS and EPS, which is the minimum number of points, and the radius are the 2 parameters of this method that can be adjusted in order to explore different clustering solutions. It's often an advantage to combine hierarchical cluster analysis with non-hierarchical cluster analysis in order to utilize the advantages of both approaches. I'll now go through some of the advantages and disadvantages of these 2 main types of clustering algorithms. The advantages of hierarchical cluster analysis is that the dendrogram offers a simple but comprehensive portrayal of different clustering solutions appearing at different distance thresholds. And this is very useful for choosing the number of clusters to use. Hierarchical cluster analysis can be applied to almost any research question, and it's also fast to run. The disadvantages of hierarchical cluster analysis is that the dendrograms are most useful when there is a small number of observations. Otherwise, the dendrograms become very large and it's difficult to keep the overview. Hierarchical cluster analysis also only makes one pass through the data. Therefore, early clustering decisions affect the rest of the clustering results. Hierarchical clusters often have low stability. That means that adding or subtracting variables or adding or dropping observations can affect the groupings substantially. Hierarchical cluster analysis is also sensitive to outliers, and it may have difficulties of handling different sized clusters and convex shapes. There is also no objective function that is directly minimized. We only base the clustering on the distances between the observations. And sometimes it's difficult to identify the correct number of clusters by the dendrogram, especially if we have a large number of observations. The advantages of non-hierarchical cluster analysis is that the results are less susceptible to outliers in the data, the distance measure used, and the inclusion of irrelevant or inappropriate variables. Non-hierarchical cluster analysis can also analyze extremely large datasets, in contrast to hierarchical cluster analysis. The disadvantages of non-hierarchical cluster analysis is that even a non-random starting solution does not guarantee an optimal clustering of the observations. In many instances, the researcher will get a different final solution for each set of specified seed points. And with seed points, we mean, for example, the cluster centers in k-means clustering, which are initialized often at random. Non-hierarchical cluster analysis is also not so efficient when a large number of possible cluster solutions exist. Each cluster solution is a separate analysis, in contrast to in hierarchical cluster analysis that generates all possible cluster solutions in a single analysis. Non-hierarchical cluster analysis is not as well suited for exploring a wide range of solutions based on varying similarity measures, observations included, and potential seed points. A combination approach using a hierarchical approach followed by a non-hierarchical approach is therefore often advisable in order to utilize the advantages of both approaches. So first, a hierarchical technique is used to select a number of clusters and find the cluster centers, and then which then serve as initial cluster seeds in the non-hierarchical procedure. So a non-hierarchical method then clusters all observations using these seed points to provide more accurate cluster memberships. In this way, the advantages of hierarchical methods are complemented by the ability of non-hierarchical methods to refine the results by allowing the switching of cluster memberships. Validation is essential in cluster analysis. One way to validate the clustering results is to use cross-validation, which empirically validates a cluster solution by creating two subsamples, either by randomly splitting the sample or using leave one observation out. And then the two cluster solutions are compared for consistency with respect to the number of clusters and the cluster profiles. Validation is also achieved by examining differences on variables not included in the cluster analysis, but for which a theoretical or a relevant reason enables the expectation of variation across the clusters. We can evaluate cluster results by calculating, for example, the intra-cluster cohesion or compactness of the clusters. Here, cohesion measures how near the data points in a cluster are to the cluster centroid. The sum of a squared error is a commonly used measure used here. We can also calculate the intercluster separation or isolation, where separation means that different cluster centroids should be far away from one another. So we want observations within the same cluster to be as close to each other as possible, and we want them to be as far away from observations in other clusters as possible. But in most applications, expert judgments are still the key. Interpretation of cluster solutions involves examining the distinguishing characteristics of each cluster's profile and identifying substantial differences between the clusters. Cluster solutions failing to show substantial variation indicate that other cluster solutions should be examined. And the cluster centroid, the mean profile of the cluster on each clustering variable, is particularly useful in the interpretation stage. The cluster centroid should also be assessed for correspondence with the researcher's prior expectations based on theory or practical experience. So to summarize, clustering has a long history and is still in active research. There are a huge number of clustering algorithms. Among them are density-based algorithms, subspace clustering, scale-up methods, neural network-based methods, fuzzy clustering, co-clustering, etc., etc. And more are still coming every year. Comparing different clustering algorithms is a difficult task because no one knows the correct clusters. Clustering is also hard to evaluate, but it is very useful in practice. Clustering is highly application dependent and also to some extent subjective, as we talked about early in the lecture, where we looked at the two different cluster solutions and evaluated whether there should be 3 or 2 clusters. So this is to some degree subjective. Thank you very much.